Now we are coming back to techniques. The industrial classification of minerals. The question was, if we want to bring these, let's say, waste to the industry, we have to be clear what is the industrial classification, where to go into, and is it possible to produce something out of this material. First, what we had to learn is it is a highly interdisciplinary task. There are so many, let's say, interests which have to be combined in this sector. The one is the government. Why is the government interested to keep it as a waste? Yeah, it depends on which ministry you are going. The point is, there is an environmental ministry, and the numbers which I told you, about 100 euros per ton, is the amount which goes directly in the budget of the ministry. So they have no interest to get out of it. The other is the Ministry for constructing of the tunnels or the infrastructure. They would be highly interested to get out of it. We, outside of the ministry, say, does it really make sense to transfer the money from this ministry to this ministry? But our view maybe is not big enough to understand what is going in there behind. I just wanted to say there are different interests from different ministries. There are NGOs. NGOs want to see that we are going in an environmental friendly way, following all these European legislation. There are investors. When a line comes up, I don't know how it is here in Argentina. When the first line is coming up, we are building a line from here to there, and it is clear where the portal areas are. The investors buy these places of land. They are the first who are buying this land because they know we have to deposit something, and then we, construction industry, have to pay all the money to these who are the owners. The construction industry in Austria is not really interested in this topic. They fulfill what the client says. In other countries, this is a little bit different. Germany, for example, because we have a design-build contract. In Germany, they have a design-build contract, and this topic is shifted to the construction industry. In Austria, the construction industry has to fulfill what the client says. The client is very strong, has engineers in, and they are mainly the construction site managers, let's say it in this way. The mining industry is an important field because the situation is as I described already. They say, you are having waste, I take it, but please pay the amount a little bit less than for depositing, but please pay the amount to me, then I take it. We wanted to go another way. We wanted to get some money from the mining industry for this good product, but as the legislation is as it is, there's no way for the moment. The consultants, I would say they are not really interested in all these things for the moment, because they say, if I deal with getting out it from this waste regime, I have much more work than if I follow deposit it here or there. It's the much more easy way. It's more costly, but it's easier. And we have to train the consultants on all this legislation and also the global warming potential. And so I would say the designers, for the moment, did not follow these new developments of environmental friendly aspects in the design. We need the next generation for that. The older designers are focusing on UCS, friction angle, Young's modulus, static, okay, fine. Of course, these are different aspects, and that's why it's really hard to shift the topic further. I mentioned almost similar slide also in the morning. There are technical aspects to be considered, geological ones, legal ones, this is the hardest, and economic ones. Technical ones. Now, if you do it with drill and blast, you must be clear that you bring in your chemicals from the blasting into the excavation material. And you have to have a site organization who can then handle that. You need somebody who detects what is the, let's say, chemical consumption of your excavation material. You need somebody for that. You need, for the moment, big places to store your excavation material at a place until you know what is in this big mass of excavated material. Before you don't know what it is exactly, you will not be able to deposit it here or there or bring it to the industry. So our problem is the analysis, which we have to do following all this legislation, takes a lot of time, in average 2 weeks. So you can imagine, you bring out your excavated material, you have to intermediate store this on a place until you get the results from the laboratory so that you can bring it anywhere. This brings me then to my last presentation, and you will see what we are working on. Because this needs huge places for intermediate storage. The other things I think is clear, geology, economic aspects are, of course, essential. If there is no industry near your construction site where you can sell it, then it gets completely out of interest of anybody to transfer your excavated material to this industry. So it must be economic at the end. The slide, what I show you here, is just to give you a feeling that we can, and the mining industry does, use the excavated material, simple example, limestone, for many reasons. For example, limestone is needed for producing soda. Limestone is the basis for gypsum products. Limestone is also the basis for etune, which is a chemical, let's say, substance. Is also a basis for slaked lime products. It's also a basis for the cement industry, and a basis, of course, for building materials. And limestone, I would say 50% of our projects consist major parts of limestone, but for the moment, deposited. I want the rows, what you see here, granites, acid vulcanites, basic vulcanites, limestone dolomites, marble and metamorphic rocks, are the most common geologists, lithologists in our area. And if somebody says, yeah, what should we do with that? Please have a look in the mining industry, what they do in Austria with these materials. We have mines for all of these lithologies, and what they do with it are the columns. So everywhere where you see a colored area, we have exactly for that granites, for example, of course, aggregates for concrete. Why are we then bringing our granites on the deposit? On the other hand, we have a mine very close to the construction site and bring it to the construction site. So there are different possibilities to use it. This brought us together with the ministry in the year of 2015 to the point that we wrote a guideline what has to be fulfilled in future, and we did a separation of typical industrial products, let's say, which have now any numbering, which you can see on this slide here. And the design consultant must do, is not a, yeah, I will do or I want, is a must. He has to do in a preliminary stage a plan where he says, this material from my exploration will be this and could be used for that. And he has to sort one of these H-numbered uses. And if he says this material cannot be used for anything, then it gets a D, D standing for deposit. It's his duty in the earliest stage of a project development to make a plan like this. Oops, like this. What you can now maybe hardly read is the lines which are following the longitudinal section are the H names, which means this is an industrial use, possibility of industrial use. If he gives it a red color, he says it cannot be used for this. If he says a yellow color, it says it could be, if the consumption is this and that, it could be, and if it is a green color, he says it's for sure possible to make this industrial product out of this material. The design consultant has not the duty to say it's economic. He should focus on, is it technically possible, yes or no? And he has to do that for all possible products what are written in this guideline, and this is very broad. If he says it has to be deposit, he has to say how much of this section has to be deposited, and in which class of deposit. The deposits are very different in the cost. There is a reactor deposit, there are different kinds of deposit. This is the numbering of the deposits. And the last three lines, which are shown there, are saying the following. I had the possibility to do enough exploration. So if he says the client gave me enough information or he gave me enough money that I was able to do the exploration in a sufficient way that I can fulfill the table above, he gives a green light. If he says too less, I cannot do something with this information, the client didn't allow, I don't know, core drilling, geophysics, whatever he needs, then he gives it a red sign. The ministry must know that the client says, yes, please do it, or we don't have the money for that. It gives a green or red light, very clear. And if he says, yeah, the client allowed me to do this or that, but it wasn't sufficient, it gets a yellow light. It is interesting for the construction industry which follows, because the construction industry can then say, okay, if the client didn't do that, maybe I do it on my cost, then the product belongs to me and I sell it. But it is a clear sign the client is, let's say, environmental friendly, yes or no, the first line. The second is how risky is the geology. So it could be that he got a green light, the client said, okay, we do core drillings, lots of them, but the geology is such complicated that even though there is a big risk left, then he says there's a big risk, red light, there's no risk, green light, or something in between, yellow light. And this gives a safety of prognosis. This is the last line in this plan which he has to do, that he says, my prognosis is on the safe side, green light is not on the safe side because I hadn't enough sufficient information or is in between. And this plan has to be done in every stage from now on, from 2015 on, so that we get, and is focused not on statics, not on anything, but just on resource efficiency, environmental friendly tunneling. And this is a must in every contract. So we force, so to say, the client to go, the client, but also the design consultant, to do something on that. Now, we have aggregates for concrete production. I don't want to go too much to the details. You get the slides, I think. And for example, we have to do a laboratory. The guideline says you have to do a laboratory test with the material, uniaxial compressive strength. For concrete production, our experience is that the material has to have at least 40 megapascal. If it is lower, you cannot use that material for concrete production. So that the design consultant gets numbers, okay, I can use it or I cannot use it. So he has a guideline where he can look into. This is of course just a short excerption of this guideline, is a full list. He should test the E-module, Young's modulus. The quantity of samples, what he has to have is 30 tons, by the way. This is written in the guideline. If he doesn't have 30 tons of material available, we say it's not sufficient. Of course, the material has to be taken from a lithology which you find on the surface, because 30 tons on core drilling is a little bit hard to compete. So 30 tons is the minimum requirement on each lithology. This is very clear stated, and if the client doesn't allow to do that, he can make a red light and say the client has no interest in that. Sorry, I cannot. Just example, the Gotthard base tunnel, which was 2 tubes, 57 kilometers long, had 28 million tons of excavation material. The mineral resources which were used for concrete production were 6.5 million tons. And in all, they produced 3.3 million cubic meter of concrete. I would say this is a first really good example where they did it. And the client, this is what we liked very much, the client took the full responsibility if it is possible to make this concrete out of the excavation material. In percentage, I mean, this is already long ago, 23% of reused material. This is a high amount. The Lötschberg, 2 times 35 kilometers, excavation total 16 million tons, mineral resource which was used 3.8, concrete 1.9 million cubic meter, 23%. Lyon-Turin is not built, they started already. Again, 2 times 57 kilometers, total excavation volume 30 million tons. It is foreseen 9.7 million tons to be reduced to produce 5.5 million cubic meter of concrete, if possible, would be 28%. So this, I think, drives in the right direction. Another example, if we take the Gotthard again, suitable for concrete production would have been 36%. And they did, as you see, out of this 36%, they did 29 for concrete aggregates. 2.5 even supplied third parties. This we would like to get up more, bringing this material to the industry. Losses during the processing, 2.5% in sludge, which had to be deposited 2%. The own usage for embankments was 19.6, landfill recultivation 30%, fill material for third parties 14%, and reactor, the repository, because this is the most awful waste, 0.4%. This is the most expensive. As time is running, I don't want to go too much into the industrial production. On this slide, there are elements which the industry gives, depending on the industry, which we have to check. And we set up a database which is working like that. Our university is 175 years old, a little bit more than that, and mining and mineralogy was done there for years. And these colleagues wrote down which geology contains which minerals contain which chemistry. So we have books available for geology and elemental, let's say, elemental distribution in this mineralogy. And as it is a mining chair, they said, okay, we check with all the industries what is the requirement from which industry. There are books. For example, you would like to produce steel. What kind of raw materials do you need for steel production? You produce glass. What kind of minerals do you need for glass production? And. What we did now is we put everything in a database. So we put the geological information and the industrial information in a database. So what we can do now is, if we get a chemical consumption of anything, of the excavation material, we feed it into the database, and the database can tell me this material is good for that. I lost my slide. Or is my time over, maybe? However, this database now is, for the moment, open for everybody, so you can type in whatever you use, or whatever you have on your construction site, you type it in, and the program says you can use that material for glass production, steel construction, ceramics, or you can use it for nothing. Could also be a result. Now, working together with the mining industry, we learned that we have to categorize. We made 3 levels. Level 1 is, from this excavation material of the tunnel, it is very easy to produce this product. You just break it down, crash it, wash it, and make a concrete out of it. Easiest way. Level 2, your excavation material is medium easy to manage because you require already a little bit more processing. And level 3, even if the database says, yes, you can produce steel out of it, it is so hard to produce it because you need a manufacturing unit, you need processing units which you will never have on a construction site. Then we put a red light to it and we say, okay, the material would be good, but we will never set up a processing unit on the construction site with this. These are the 3 levels. And now, just an example again. For example, limestone. Limestone can be used for big iron. We gave it a red light because we will not start to produce the components for big iron on a tunnel construction site. What we could, let's say, imagine is that we give these to somebody who produces big iron. But it's much too complicated to do it on a construction site. Calcium carbide, a yellow light, it is an effort to do that. And if you have just little mass, it will not be economic. Glass, red light, for example. Cement production, green light, it's easy to bring it in a form that you hand it over to the cement production. That's how we did it. So database tells you this can be made out of it, and then a categorization from green, yellow, red can be done with an effort which you can do on the construction site, or it's better to hand it over to a mining processing unit. Just examples on this classification chart. To make you a little bit familiar with this, what is the industry telling us? For example, polymers. The polymers need limestone. And then it says limestone is not limestone. Limestone consists of CaCO3, calcium carbonate, CaO, calcium oxide, and then everything is in limestone. And the industry gives very clear ranges from to where you can use it for producing, for example, polymers. And the database has already incorporated all these ranges so that the database now tells us, okay, can be used for polymers, yes or no, or can be used for sodas. These are just examples which are given here. And treatment effort, hard, easy, or very hard. Now, I mentioned already, economy plays a major role. We tried to do that with a project in the French part of Switzerland, and the outcome was the blue line. It is very much depending on how much do you produce. Because you have to buy your processing units, a sieve, a crusher, a washing unit, whatever. And the more you produce, the cheaper the ton gets. And in the easiest processing, it's the blue line, and in the hardest processing, it's the upper line. And then you can have a look how much is the material which I have to buy from the mining. If the mining is outside, then it makes sense to do it yourself. It was done on a Swiss project, and you know the Swiss almost have nothing available for mining. There is no mining anymore. So in the Swiss area, for example, it makes even sense to transfer, it would make sense if it would be allowed to transfer the excavation material from the Brenner base tunnel, which is a 200 kilometer away from Switzerland, to transfer it to Switzerland. And we would even make a business, but legally forbidden. Now, of course, we have to make a quality assurance. And how is it done nowadays? Nowadays, we do it by point load tests. These tests, what I mentioned already before. A point load test, microscopy in the laboratory, breakability tests, and so on. They take their time, and to bring the results back to the construction site is, in our view, too slow. That's why we did a European project and developed things which can give you the information of the excavation material online. And we produced prototypes for that. For example, we developed together with the company of Herrenknecht a disk monitoring system. So we bring a monitoring into the disk of the cutter head. And this disk now measures the hardness of the material on the face, which is a kind of UCS, where we say the UCS is the wrong value, by the way, but it gives you an intention of how hard is the material at the face. Then we developed an automated analysis, which I will show you in the last of my presentations, an automated analysis for elemental chemical analysis. So the material is running on the conveyor belt, and you detect what is on the conveyor belt by an automated analysis. So you don't have to wait for the laboratory tests, because in the minute where it is running on the conveyor belt, this detector says, okay, this is this and this elemental composition. And some others which I will speak then afterwards. We think this could be a driver for the construction industry, because they know it in the moment when they do the tunnel, what is the material. They don't have to wait the 2 weeks when the results come back from the laboratories. One of the hard points is the mica, because mica often is, let's say, avoiding that we can use it for concrete, because this brings the strength down. But mica is not mica, and what we saw is, and that's why the regulation of the European Union is good to standardize the test. You see here a chart of the mica content of different lithologies which were done at the Gotthard base tunnel. And you see that the mica content is depending on the grain size where I measure the mica. If I measure the mica content in a grain size, let's say between 1 and 2 millimeter, I have almost nothing. But if I measure the mica content in the fine-grained material, the mica goes up, because the mica collects in the fine-grained. And for example, here we have the mica content in sand, in a 0 to 4 millimeter sand. And the mica was measured in the fraction 0.25 to 0.5 millimeter. Austria standard, for example, says we measure the mica between 1.025 to 1.25. You see, this is another section than the Swiss does. So we cannot compare the Swiss and the Austrian results on the mica content, which is essential. If we do that, the construction company asks us, okay, can I use now this for concrete production, yes or no? You can use this product in this range of mica for concrete, but you couldn't use it if the mica is up there, because it gets much more difficult to pump the concrete, and the strength you cannot reach. And that's why it was fixed that the mica content must be lower than 35 ppm, measured in the range 0.25 to 0.5 millimeters. And all of this information is essential, because sometimes here, okay, I have 40% mica. What is it? Volume percent, mass percent, piece percent? No information. Where did you measure it? No information. But this is essential. That's why the standardization which the European Union gave us is good on this side, because then it's clear we have to measure it here in this range, and it is not volume percent, not mass percent, it's pieces percent. This is good. Mineral base, the database, because of the time I go over that, is a database where you can use it as I described it before. Just to tell you an overview here, the red points are the plants, are the industries which are using minerals, and the blue are the tunneling sites. And you see just from these charts, the industry is not so far away from our tunneling construction sites. So why shouldn't there be a chance to reuse it? Yeah, I go over that because of time. I would say there is a possibility to use the excavation material, but it must be driven by the designer. The designer must give the opportunity to check all of that to the design consultant. The design consultant has to get the knowledge in the offices, because there is a learning procedure nowadays. It will be the younger generation which will work on that. I would say just do it. There is a chance to do it. That was my presentation on that, and one more follows. Thanks for listening.